Hello, how's it going, everyone? I hope the test Monday went well. Alright, if you're watching this video and you haven't submitted your test yet, well, please go and make sure it's done and that you have submitted it. Make sure you double check. Alright, I'm hoping to get those back to you guys by Monday. So the way that's going to work is I'm going to post something called a rubric on Google Classroom, and that's going to have a breakdown of each question and the number of points it could have gotten on each question. And the only feedback you're really going to get is the number of points you got on each question. So if you lost points on a certain question and you're not sure why, just let me know on Google Classroom and I'll reply back with a comment letting you know how come you lost points, if you lost any points at all. Alright, and that was also my first online test. Alright, so if you have any feedback or comments about what I could do better, or you thought it was a good test, it was too easy, it was too hard, too long, too short, I gave you guys too much time, or stuff like that, just send me an email, and I'm really open to hearing what you guys have to say. And yeah, so if you let me know what I can do better, I can make it better for the future. Alright, so I done after the test, we'll do something that, it's a little different. But we're going to go back to exponentials after this, but I thought we might as well fit it in now. We're going to be doing inverse functions today. So what is an inverse function? And I have this cute little diagram. So this diagram pretty much shows what an inverse function does. Alright, so if we have some function, f, and this function f takes an apple and transforms it or turns it into a banana. If we now take this banana and we put it into this thing, f, which looks like to the power of -1, that is not to the negative first power. This is our notation for a inverse function. Alright, so like if you have a function f of x, the inverse would look like that. Alright, and just like we know f of x does not mean f times x, alright, we should know that this has nothing to do with the negative first power of something. Alright, it's just the way we write inverse. Alright, also does not mean reciprocal, right? Does not mean you make it 1 over f of x or anything like that. Right? Has nothing to do with the power -1. It's just the notation for inverse function. Alright, so what this function is pretty much doing, this inverse function, it's essentially taking our output of the original function, right, and making it back into an apple. So we can say that an inverse function I'm going to put this in quotation marks because it's not really precisely a mathematical term, but an inverse function reverses or undoes another function. And that's really the simplest or most concise definition. So let's do this with, instead of apples and oranges, x and y. So if I take some input x and I input it into this function f, right, I'm going to get out outputs, or y. So now if I take those outputs and I make them my inputs for this other function, which let's call it the inverse function, well, if this is the inverse of function f, this will give me back the original inputs. So essentially it's the same thing as the apple and oranges. I could have put it like this, right? Make it all one line. That's exactly the same. But I want to make it 2 lines just so we can see that, well, if x were the original domain, right, my inputs, well, the outputs, that's going to constitute the range. And if y is the range, well, there's y over here, right? the range of the original function becomes the domain of my inverse function. And the domain of my original function becomes the range of the inverse function. So not only are we reversing what the original function does, but it looks like the domain and range are also reversed. So let's say we had this relation over here. Right, we have inputs and outputs. So let's pretend this were a function. It is a function, but let's call this function f, for example. And this function, if I input a 1, right, I get out a -3. So that means in the inverse function, if I input a -3, it should give me back out a 1. Right, so the inverse to this relation over here, it's literally just going to be the same points except flipped. So instead of -2, 3, it's going to be 3, -2. 5, 1 will become 1, 5. 6, 4 is going to become 4, 6. Alright, this is pretty much saying, well, this is saying, in the original, if I put in a 5, I get out a 1. Which means in the inverse, if I put in a 1, I'll get back out the original 5. And as you can see, the domain of the original function was domain of our original function. I'm just going to call it f. That was 1, -2, 5, 6. And if you take a look here, the range of our inverse function, what is that? Well, that's 1, -2, 5, 6. Right, so just showing this fact here, right? If I found a range of the original, that of course would equal the domain of the inverse. All right. So how can we get the equation of an inverse function? We want a function where we're taking all the inputs and, well, we want a function where in the original function I have inputs and outputs. When I take those outputs of the original function, I want back the inputs. So I want to reverse this function f of x. So let's think about this in words first. In words, this function is telling me to, well, x is my inputs. This is telling me to multiply the inputs by 2. Right? Multiply the inputs by 2. And then add 5. So what is going to be the exact opposite of this? What is going to undo this process of multiplying inputs by 2 and then adding 5? Well, the opposite of that is we have to do it in reverse order as well. We're going to subtract 5 first. Subtract 5 from the inputs. And we multiplied the inputs by 2 first, so now we're going to divide by 2. So according to what we're saying here, our inverse function should look like this. Here's the notation. The inverse of our original function is going to equal, so I'm subtracting 5 from the input, so x minus 5, and then I'm going to divide that entire thing by 2. And that should look like the inverse function. So we're not going to be doing it this way. This is just a way to think about what the inverse is. So the way to get the inverse function is we're literally going to swap the inputs and outputs. because that is actually what is happening when you look at this. Right? The outputs become the inputs, and the original inputs became the outputs of the inverse function. So literally we're going to swap x and y, or f of x. So the first step is we make f of x y. And we just do that so it's easier to work with. And then we literally swap the positions of x and y. And so it becomes x and y like that. So x equals 2y plus 5. And now we're going to solve for this new y here. And that y is going to become our inverse function. So solving for y, we get x minus 5 equals 2y. Divide both sides by 2. And we get x minus 5 all divided by 2 equals y. And isn't that what that looks like? Right? So this process of switching to x and y and solving for the new y, that is really undoing what the original function is doing to the inputs. And the last step, quite important, is to replace that y with the inverse function notation. So now we're saying the inverse function to our f of x function is x minus 5 over 2. Right, so let's graph both of these and see what they look like. So f of x was 2x plus 5. So I'm going to scale everything by 1. 1, 2, 3, 4, 5, 6, 7, 8. So up 2 over 1, up 2 over 1, down 2 left 1, down 2 left 1. And I'm just going to keep going a little bit. And I'll connect these dots. Does that look good? Okay. Alright, so that's f of x. My inverse function is x minus 5 over 2. If I want, I can write it as 1 over 2x minus 5 halves, or 2.5. So if I go to negative 2.5, that's over there, and I know the slope is a half. So that means I'll have this point, and I can go up 1 over 2. Up 1 over 2, up 1 over 2, up 1 over 2. At this point, they're going to intersect there. And there's my inverse function. This here is the inverse of f of x. Alright, so graphically, what do you notice about the inverse functions? Well, hopefully from geometry, this is a transformation, right? Think about what transformation we can do to f of x to get the inverse of f of x. So if you're saying this looks like a reflection across a line that looks like this, you would be correct. This is actually a reflection over the line y equals x. The inverse function is a reflection of f of x over y equal x. Right, I can put that over here for letter B. What do you notice about the inverse function? Singular, not plural. And if you remember from geometry, when you reflect over y equals x, you switch the x and y values. They flip-flop. So let's take a look. I'm just going to plot some points, or label some points. This point is negative 2, 1. So if I reflect that over y equals x, that point should become 1 comma negative 2. And do I have 1 comma negative 2? Yes, I do. If I have this point over here, this looks like negative 1 comma 3. Right, doesn't that become 3 comma negative 1? And there we go, that's the point 3 comma negative 1. Alright, I'll do one more point. This point 0 comma 1, 2, 3, 4, 5. That's going to become 5 comma 0. And there it is. So I'm going to make a table here for x and f of x, just a really small table, just listing those points we have. You got negative 2, 1, negative 1, 3, 0, 5. And in the inverse function, all of those points got reversed. So it became 1, negative 2, 3, negative 1, 5, 0, etc. And this is going to be true for all points, right? Now I'm just going to plot one more. 3 comma 11 would be a point. In the inverse, that would become 11 comma 3. So this letter C here asks, how can we algebraically confirm that these two functions are inverses? Well, yeah, so this is like an algebraic way, but I want you to notice that this is the same as that, right? And this is the same as that. And really, we know this already, right? Because the inputs became the outputs, and the outputs became the inputs, and the domain and the range, they switched. But a way we can express this nicely mathematically is that these f of x values, right, are now my inputs. Those are the same. So if I plug in f of x into my inverse function, think about what this is going to equal. So I think it's easiest to see in the table. So again, I plugged in random x values into my first function, and I got these values, these outputs, right? These f of x values. Well, these f of x values have now become the inputs to my inverse function. So that's what I'm showing here. When I take the original function and I input it into the inverse function, well, what do I get out? I get out something that looks like the original inputs. So that's going to equal x. So anytime you compose an inverse function with its original function, you get out x. It's just going to equal x. And this will work the other way around as well. You can do f of the inverse function, and that is also going to equal x. For the same reason, we're just going to go in reverse. Alright, so I'm hoping this makes sense, because this is actually another way we're going to algebraically confirm that these two functions are inverses. So let me copy down the two functions. F of x was equal to 2x plus 5. And my inverse function was, what was it? 1/2 x minus 5 halves, or x minus 5 over 2. Alright, so let's take a look at what f of our inverse function is equal to. So this means we're taking our inverse function, which is this, which is x minus 5 over 2, and we're going to plug it in for that x. Alright, so I'm actually going to rewrite this one step I'm going to replace my inverse function with what it's equal to, which is x minus 5 over 2. So now we're doing f of x minus 5 over 2, and that's going to equal, so I'm taking x minus 5 over 2, right, and I'm plugging it in to the original function, and for that x. So that's going to be 2 times x minus 5 over 2 plus 5. When we multiply out the 2's, that's going to cancel with the dividing by 2. That's going to equal x minus 5 plus 5. And we know we've done it correctly because when we composed the function with its inverse function, we got back out the original inputs. Alright, and so pretty much what we're doing is this. Right, we're composing the two functions together. I'm using my inverse function. I'm inputting the original function, right? This would be like f of x. And I get back out the original values of x. So graphically, we know inverse functions are a reflection of over the line y equals x. That can be hard to do. But we also know reflecting over y equals x means flipping the x and the y values. So 1 comma 0, for example, would become 0 comma 1. Right? This point here, negative 1 comma 0 is going to become 0 comma negative 1. That'll become that point. I'm looking at the original black graph here. That original point on the graph would be, what is that, 0, negative 1. That's going to become negative 1 comma 0. So that point becomes this point. And I can take a couple more points like 2 comma 3. 2 comma 3 will become 3 comma 2. This point, negative 2 comma 3 becomes 3 comma negative 2. And so if I connect these dots here, I'm just going to assume there's arrows over here as well. Right, there's my inverse function. So for example, if I call this h of x, this would be the inverse to h of x. But you might be saying, this inverse function doesn't look like a function, and you'd be right because this is not a function. So just want to note the inverse here is not a function. So you'd have to apply domain restrictions if you want a proper inverse function here. Alright, and let's just think about like y equals x squared, for example. The inverse of y equals x squared is going to be the square root of x. And the reason that's a problem is because in the original function, that's defined for all real values of x. But in the inverse function, it's only defined for positive values of x, or 0. So for Algebra 2, we don't really need to worry about this, but this is something you have to go into detail about in pre-calc. Alright, but just know we have to apply domain restrictions. So if I made h of x only for values of x greater than 0, then we would have a properly defined inverse function. It would look like that. Alright, but that's not for this class, so don't worry about it. Again, we're just flipping x and y values. I'm just going to make a quick sketch here. Negative 1, 1 is going to become 1, negative 1. It's going to become this point. 1, negative 1, which is that same point over there, in the original would become 1, negative 1 becomes negative 1, 1. That'll become that point. 0, 0 becomes 0, 0. Might be thinking the function looks the same, so let's get another point. Let's take this point, for example. this looks like negative 1.5 comma 3. That's going to become negative 1.5 comma 3 becomes 3 comma negative 1.5. That's going to become that point. And 1.5 comma negative 3 will become negative 3 comma 1.5. That's going to become this point. So the function actually looks like that, our inverse function. I'm going to assume there's arrows at the end. Boom. And I probably should have made this a little more curvy, but hopefully you get the idea. Here's our inverse function. And, alright, I'm not going to do the rest of these. All you have to do is pick some points and flip the x and y values. Right, if you want, you can draw in y equals x to help visualize what's going to happen when you reflect over that line. But I have a hard time doing that, to be honest. So I just take all the points and switch the x and y values and plot them. Alright, yeah, I'm going to skip those last two. Alright, so number 4, f of x is equal to this. I probably should have written some instructions here. And so the instructions are, what's the inverse function equal to? So I want to write down some steps, right, to find the inverse function. Here's what we do. So it's exactly what we did before. We're just writing it down, the directions or the steps for this. So step 1 is we're going to change f of x to y. We're going to use the word physically. We're actually doing this. We're just swapping x and y. We're physically going to swap x and y. All right, step 3 is we're going to solve for y. And then the last step is you replace y with the correct notation for the inverse function. Alright, so let's do this example. First step, f of x becomes y, and there's our function. So step 1. Step 2, we swap x and y. So I know there's two x's, alright, but our input x becomes our output, right? And our output in the original becomes the input of our inverse function. So that's what's happening. All right, copy the rest of it down. All right, step 3, solve for y. So I have y in two places here. Hopefully you remember you can't divide or do anything weird like that. So I'm going to cross multiply first. X times y minus 4 equals y plus 2. All right, and why don't you guys take a minute and pause the video, see if you can finish solving for y now. Alright, so hopefully you gave it a shot. But we got y in two places here, right? So let's try to get both of these y's on the same side of the equation. So if I distribute that x, I get x times y minus 4x equals y plus 2. Right, I'm going to group these y's on the same side, so I'm going to minus y on both sides. Xy minus y equals, I'm going to add 4x to both sides at the same time, 4x plus 2. And now that y's are both on the same side, think about what we can do to isolate for y. That's right, we can factor it out. Y times x minus 1 equals 4x plus 2. And if you divide both sides by x minus 1, we get 4x plus 2 over x minus y. And our last step is, this is our inverse function. replace y with the inverse function notation. And that is it. So the trickiest step here is solving for y. Right, sometimes the equations can be a little challenging, usually not too bad though, just like what we did right now. So solving for y, you might have to get the y's on the same side and undistribute or factor it out. But there we go. Right, so I'm actually going to graph these two on Desmos real quick. Give me a second. So y equals x plus 2 over x minus 4. Oh yeah, you guys can see it here. So you can always check to see if you're correct by graphing. Alright, first function, y equals x plus 2. Divided by x minus 4. Y equals 4x plus, I'm sorry, I gotta look back real quick, 4x plus 2. Divided by x minus 1. So take a look at those two guys. And let me also graph y equals x. And hopefully you can see that does look like a reflection over y equals x. Alright, I'm also going to convert both of these into tables. And hopefully you can see all of the points are flip-flopped. Input became outputs. Right, negative 2 comma 0 up there became 0 comma negative 2 down here. Negative 1 comma negative 0.2. Well, if I input a negative 0.2, negative 0.2, right, I get out negative 1. Negative 1, 0, negative 0.2, negative 0.2, negative 1, right, etc. So, looking at the table, we can see exactly that these are inverse functions, right? One of these functions will undo the other function. So, just one more example. Again, we're going to find the inverse, then I want us to use a g to the inverse. So, find the inverse function g of x here. So we're naming the inverse function g of x. So first step, y equals x plus 7 over 2x minus 1. Swap x and y. X equals y plus 7 over 2y minus 1. Going to cross multiply. 2xy minus x equals y plus 7. Group the y's on one side, so 2xy minus y, going to add x to both sides, x plus 7, factor out y times 2x minus 1 equals x plus 7, y equals x plus 7 over 2x minus 1, and this is our inverse function. They asked us to name it g of x, so the inverse of f of x equals g of x equals x plus 7 over 2x minus 1. So, you might be looking, f of x looks like g of x. Well, they are because they're the same function. So, this function is an inverse onto itself. This function undoes itself, which is kind of cool. So if you want to really check, we can see does f of the inverse function equal x, right? So this is how we're going to confirm by a composition that this is correct. It's kind of a way of checking our answer. So the inverse function, in this case, we called it g of x. So if I take g of x and I plug that into my original function, that should be x. Well, what am I plugging into the original function? G of x was x plus 7 over 2x minus 1. And so that's going to equal f of x plus 7 over 2x minus 1. So I'm taking this and I'm plugging it into itself, right? I know this one's kind of weird because it's the same function, right? But I'm taking this and I am plugging it in there and there. Alright, so if you want to give this a shot, you already know the answer should just be x. So that's a pretty cool one to try out. But doing this, I will have x plus 7 over 2x minus 1 plus 7 all over, on the bottom, 2 times x plus 7 divided by 2x minus 1, close parentheses, minus 1. So I'm sure this is bringing back some good memories. We got some complex fraction here. So I'm going to do it by multiplying everything by the LCD of the top and bottom fractions. But before we do that, I just want to distribute out that 2 on the bottom, make that 2x plus 14 over 2x minus 1 minus 1. So if I look at the top and the bottom, right, I have 2x minus 1 in both denominators of those smaller fractions. So the LCD of all 4 fractions is just 2x minus 1. Right? I can make this 7 over 1 if I want. Make that 1 over 1. But I can multiply by 2x minus 1 over 2x minus 1. Right? I'm multiplying by a value of 1, not changing it. And that's going to eliminate all of the fractions. Right? Again, if you don't like my method, you can make the top 1 fraction, you make the bottom 1 fraction, then you can change it to multiplication by the reciprocal. So, anyway, distributing this 2x minus 1 over the top, the 2x minus 1's cancel out. We get x plus 7 plus 7 times 2x minus 1 is 14x minus 7 all over, distribute the 2x minus 1 to both terms on the bottom. We get 2x plus 14 minus 1 times 2x minus 1. Make sure you distribute this minus over here. So that'll become 2x plus 1. Let's combine like terms on top and bottom. We get x plus 14x is 15x plus 0 all over 2x's cancel out on the bottom. 14 plus 1 is 15. Ho ho ho, we got x. Right? The composition of the function with its inverse was equal to x. We have confirmed it. Yes, check. Alright, and that was it. I think this is usually a pretty, I guess, I don't want to say easy, but it's not a difficult concept to grasp, really. Right? Inputs become outputs, outputs become inputs in the inverse function. The domain becomes the range becomes the domain. Right? It's a reflection over y equals x. Those are all properties of inverse functions. Right? And this is a way to confirm by composition. So, yeah, that's going to be it, guys. I'm going to try to do more Zoom lessons because I actually really do miss going to school. And yeah, hopefully I'll see you guys before the end of the year. All right, I do miss seeing you guys. So stay safe, take care. All right, have a good night. Bye-bye.